Hello everyone, this is Engineer Selassie from VLO Academy in Brain Boosters, and I came up with another chapter. This is chapter 14, Memory APIs, Operating System from System 3 Z Pieces from Andrea in Remzi book. So let's get into it. So the process memory usage. We know that at runtime, a process is allocated memory region, page for code, data, stack, heap. We have seen that in chapter 13. Code and the data normally do not change. Okay, the code and data normally do not change. Pre-allocated at loading time, no allocation and deallocations. And stack changes during function calls, short-lived allocation, because stack is short. Once you lose the power, all the data you store in the stack will be lost. So used to store function parameters like local variables and return addresses. Memory in this region are allocated or deallocated by manipulating the stack pointer. So we have register push using push and pull pop instructions. So implicit management, the compiler generates the push and pop, the C. Heap, in the heap it is long-lived, not like stack. Stack is short-lived, okay? So in the heap, explicit management, allocation and deallocation handled by a programmer via some APIs. So challenging to both system and programmers. So we use malloc, means memory allocation. We use this for dynamic allocation in our memory. So if you see this simple code, C code, void function, just the stack we have here, int, pointer x, int, memory allocation, and we have the size of the int. So this is the simple code. So memory APIs, the first API is malloc. This is, as we have seen now, we have include this stdlib, and we have void and malloc and the size of size. This allocate a memory region on the heap, not in the stack. Okay, this allocates in the heap. Argument size t size, this one size t size of the memory block in bytes. How many bytes you need, you have to mention here. And size t is an unassigned integer type. Okay, and in return success, a void type pointer to the memory block allocated by malloc. Otherwise, if it fail, a null pointer will be the return of our program. So memory API size of, as you can see, these returns and macros are utilized for size in malloc instead typing in a number directly. Two type of result of the size of with variable. We have the actual size of x is known at runtime. For example, int, the pointer x, malloc 10, the size of int, and this one, if we print it, what it does is it will print the size of the variable, that is 4 bytes. Okay, for our x variable. Okay, because x is a variable, so we're gonna print 4 bytes. But the actual size of x is known at a compile times. So if you write int x 10, so what it does now, it will multiply 10 by 4, and it will print the size of x in this time is it will become 40 bytes. And be careful with strings like malloc strings s plus, we need was +1. This is also So when you write your code, be careful how malloc 10 like this, or if you directly assign x to 10, then it will have different result. Memory API, the other API, we have free. So this, as you can see, include restricted, void free, void pointer. So free a memory region allocated by a call to malloc. Malloc will provide memory, free will free that area. So argument void, then asterisk this pointer, a pointer to a memory block allocated with malloc. Return none. So let's see the mechanism of memory allocation in the heap. As you can see, this is a pointer. So what it does is, for example, we have address space here. So if we local variable, if we say int pi, as you can see, if we point here, so what it does is look, this is the pointer 2 kilobyte, as you can see here, 2 KB. So this 2 KB will be directly, this is a pointer, so it will go up and it will start from 2 KB, then it will add, okay, because we are assigning a pointer here, local variable, so that means int malloc size of the integer is 4. Okay, so what it does is 2 kilobyte plus 4, because the variable the size we need is 4, then it will be allocated in this region, then again the next 8, then the next 12. So 2 kilobyte plus 4, 2 kilobyte plus 8, 2 kilobyte plus 12. So this is the way how the pointer does. Okay, it will point here and it will allocate it like this. So this is the mechanism of the memory allocation in the heap. Okay, int and this is how the pointer will be allocated. This is just a mechanism. And memory free, if we want to free a memory, then what it does is free pi. Okay, free the pointer, then what it does is directly it will go, so as you can see in the address space, it will be invalidated. Okay, so the pointer is here, so we have 2 kilobytes, and as you can see, all the 4 locations are freed. Okay, that is what the free mechanism. Now let's discuss about common errors concerning memory. Okay, the first common error is forgetting to allocate memory. Okay, the first is forgetting to allocate memory. So this is an incorrect code. What does it mean? Let's see this code. Character, we have src, hello, character string constant. Then destination, dst, this is unallocated. For example, for the destination, when we str copy destination and the source is called, okay, str copy, so we need the destination and we need the source. So what you can see is when the destination is unallocated here, dst unallocated in this situation. Okay, so the source file is hello, yeah, the source file is hello, but the destination is unallocated. This is the first problem. So I think we have code. Okay, so let's demonstrate what this means. Okay, let's demonstrate. This is called segmentation fault. Okay, because we forget to allocate the size. So let's go to our Linux. Okay, let's go to our Linux. let's open it. So we have these files. Let's open it in terminal. Okay, let's see our file. So what we want to show you here, is no malloc. For example, if we don't before no malloc, if we don't allocate so let's view, for example, no malloc.c. So this is a code, as you can see. Okay, this is a code, stud.o, stud.lib. Then we have this character hello. The character is the source is hello and the dst is here. Then we star copy is called destination and source, but we didn't assign. So what if we compile this? Let's see, gcc no malloc.elf and no malloc.c. Then let's invoke it. So as you can see, we have a segmentation fault. Okay, we have a segmentation. That means we forget to allocate the code. But what if this is a code as we have seen, and the error also we have seen now, forgetting allocation. So what happens, how to correct this problem? So what we can do now in the destination, now as you can see in the destination, we can allocate a memory. Okay, we can allocate a memory and +1 as well, as we have seen. So now it will work correctly. So what we are going to do, as you can see, the address space is here, so the source is hello, and now it is allocated. So when the code, when we call star copy this code, now as you can see, the source code is hello and the destination will be hello as well, because we already assigned the code. So let's see that. So what we are going to do, let's see the view no malloc corrected. Okay, corrected.c. Now in this case we allocated the address, you see, in the memory. Okay, we allocate. So what we are going to do, let's run this code. Malloc corrected totals malloc corrected .c. Now malloc corrected totals. Yeah. So now we don't have any problem. Okay, we don't have any problem. So the code is compiled. Okay, the code is compiled. We don't have any segmentation problem and anything, as you have seen already. It is compiled. So this is the correction for the code. Okay, so let's continue. So the second problem what we have is not allocating enough memory. That means incorrect code but work properly. Buffer overflow, we call it buffer overflow. So if you see this code, character source hello, character string constant, character destination, we allocate malloc, but the issue is we didn't allocate too small memory, because if you see we have 6 bytes here. Okay, we have 6 bytes. The source is 6 bytes hello, and we have also non-string character, but in the destination we have only 5 bytes, so we forget the non-string character. So in this case, when we call the stir copy, okay, stir copy, it works, but the memory is not enough. Okay, the memory is not enough. So let's see this. Okay, buffer overflow. So what we are going to do, we have the code also. This is buffer overflow. So let's compile it. Okay, when we compile it, it will work. Let's see. Buffer overflow gcc as you can see, the code is working. Okay, buffer overflow, as you can see, it is working. So elf, the code is working, but as we have seen here, where we assign only 5 bytes. Okay, that's not enough. That's not enough. So that is the idea of buffer overflow. So make sure that you allocate the enough memory as per the source code. The other problem we face with memory is forgetting to initialize. Forgetting to initialize. That means we forget to initialize. For example, this is a code encounter an uninitiated read. For example, this is int, we have a pointer x int, we have malloc size int allocated, and printf this uninitiated memory access. So what happens is, this one is value used before free, because this area first is not initiated. Okay, uninitiated. Okay, so when we use this code, as you can see, allocated with value used before. So already this value is already used. So we are not sure that what happens. Okay, so so the third one is forgetting to initialize. Yeah, so as you can see, encounter uninitialized read. So we have this code int pointer with x, int malloc size we already provide allocated, but the problem is uninitiated memory access. So if this problem happens, what is going to happen? Value used before free is here, heap, and we have stack, and we have the pointer here. So as you can see, when we try to allocate it, the value used before already. So allocated with value used before. So this is a problem, and I think I have code. So this code is uninitiated. As you can see here, we have which one? Uninitiated. Yeah. read.c. So let's see what's going to happen. Okay, so the code is if you want to see the code, view and nit read.c, and what I want to check, this is a code, as you can see, uninitialized memory access. So let's go back, and I think let's compile it. Let's compile it. Let's compile it and it read dot else, and we have nit read dots. So it's already compiled, so let's initialize it. Nit read dots. So as you can see, it's already 0. It shows 0. And this is the code in the textbook, and I encourage you to go ahead and check the code yourself. So the next will be error. Error 4 will be memory leak. Memory leak. What does it mean, memory leak? We allocate a lot of memory, but we never free those allocated memories. Then a program runs out of memory and eventually dies. So what it does is unused, as you can see in our memory. For example, we allocate. This is the allocated memory. This is allocate. So unused memory will continue. You see, this is unused part. This is only the allocated. This is free. So this is a used part. So through time, this memory leak means we forget to free the memory we allocated with malloc. So let's see the code. This is a simple code. As you can see, we allocated here first int with malloc. This is a pointer a, and we allocate 10, but without freeing it. Okay, without freeing it, we are going to allocate again a new 3 variables. Okay, 0, 1, 2, so 10, 20, 30. So we're gonna print the value of a, 0, 1, and 2. So this one is memory leak.else. So we have this file also. Let's clear list. Sorry. So as you can see, we have a file called memory leak dot this main leak. So first, okay, let's compile it. We see already the code, so let's compile it. Main leak dot main leak dot c. I think so. Sorry. GCC. I forget. Dot help main dot c. Okay, and main dot help. So as you can see, we it's already output, but here it prints this because we didn't remove this the first assigned pointer. So if we print this so many times, okay, sorry, if we print this code so many times, as you can see, it will print so many times. Throughout time, this will occupy space. Okay, throughout time it will occupy space, and that is a problem of memory leak. And I'll show you, we will use a tool how to identify this, but this is a problem. So when you assign a pointer and when you assign a memory to the pointer, once you finish you have to remove that area. So that is the memory. Now the other one is dangling pointer. Okay, dangling pointer. So this dangling pointer, what does it mean? Freeing memory before it is finished using or you are done with it. So we are freeing a memory before we are finished. That means a program access to memory with an invalid pointer. Okay, what does it mean? Let's say we have A and B and we have 3 nodes, 1, 2, 3 nodes. And let's say we assign A 3 kilobytes, as you can see here in our address space, and B is here. Now C is null, okay? We don't have nothing in the C. So when we assign A and B, as you can see, A is assigned, okay? And because it starts from 2K, then it will be assigned with 3 kilobytes. Then this 3 kilobytes, as you can see here, 2, 3, then we have 4 kilobytes, then 4 kilobytes. This is the circulation. But what happens is if we free B, this is B. If we free B, now what will happen is B will be free. Then there is no connection between this and this. This will be unreachable, okay? This will be unreachable. We cannot access this memory area because of we free this one. So the problem with dangling is that this node will be unreachable, as you can see, okay? So in nutshell, that is what the idea, but let's see it in code if it is clear. We have dangling C, okay? The code, if you want to see this is also in the book, you can download it, okay? So dangling.c, as you can see, this is the code, and this is allocated p int malloc size int, it's allocated, but we free p, okay? And this is another pointer with 4. So let's run this code and let's see. Let's quit this one. So what we are going to do, let's compile it, okay? Let's compile it and we shall see what's going to happen. So GCC, and what we are going to do, the dangling dot and dangling.c, and let's compile it. So as you can see, it prints 4, okay? It prints 4, okay? So in the nutshell, that's what I want to show you. So dangling effect is the idea of that when you free one address space, this is the node, then the other node will have a problem of accessing the next, so it will be a problem. So this node will be unreachable for the time. So this is the idea behind dangling pointer, and I hope the code also helped you to understand the idea. Okay, the 6th error is double free. Double free means free memory that was freed already. That is very easy. So as you can see, int x, int this will malloc, we already assigned the size and it's allocated. Then again we free x, we free x. So this repeatedly we do like that. So as you can see, address space, and it is already allocated. Then free x, it is already freed. Okay, now it's invalid. Now when we say the second time freed, so unidentified error will be encountered. Okay, I think I have code for this also. Okay, double freed we have here. I think we have double freed. Yeah, double freed we have. So let me show you. Let's see the code first. Double free dot c where is it? Okay, this is this free p. So what we are going to do, let's compile. Okay, let's compile it. GCC and sorry. Let me make it out. Yeah, double free dot f and free plus free dot f. So as you can see, this is the issue. This is the issue. Okay. So permission denied also. For example, it should yeah, because it should give us that the bash permission denied, because it is trying to free 2 times. Okay, so it should give us that. Let me try it. Free dot. Okay. Maybe I make a mistake in the code. That's why. Anyways, so that is the idea. Error 7, invalid freeze. This is also called free incorrectly used. It is dangerous. It expects a pointer as parameter that returned by malloc. So in general, you did not allocate any memory using malloc, so it's obvious to invalid. So you are trying to free the memory that which you didn't provide allocate. So in general, that is invalid. Okay. So all these memory problems are already discussed. So in real life we have tools to detect this problem. Okay, so in this discussion I want to show you Valgrind. Okay, Valgrind. This is Valgrind, and let's see the practical application of Valgrind and how it helps us to detect the memory leak. For example, this is Valgrind demonstration on no malloc C and no malloc corrector file. So what we are going to do, if you don't have the Valgrind software, you just use sudo snap install Valgrind classical, the classic, that will install in your system. I already have the system. So what we are going to do now is, let's identify the problem of the memory leak in no malloc. As we have seen, we didn't allocate memory. So if it helps us, let's see how. Valgrind no malloc. We have no malloc here. Dot. So how it will help us? Let's see. As you can see, it will give us the full report. The first report, it will check the memory error detection, and it will tell us use of uninitiated value of size 8. So at size 8, we didn't initiate the value, the size, okay? And as you can see, invalid write of size 1. It will give you a lot of information. It will give you a lot of information. Address is not process terminated with default action of sign this. If you believe this happened, so it will give you heap location in the use of exit. You see, no leaks are possible, and this track original, yes, we will use this one. So in general, what it did, it shows that there is a memory error detected. Okay, memory error for sure. Memory error was detected, and the error was here. It shows us. So now what we can do, all the problem we see done. After correcting the error, we have another malloc corrected. So let's use the same code, and this time we use the other code. Okay, you can download the code I told you. Okay, so which one we are going to use now? We are going to use the corrected one. Okay, we are going to use the corrected one. So malloc corrected. Okay, corrected alpha. So in this situation, as you can see, if you see here, no leaks are possible, and for the list of detect support error, it gives us like this, and error summary, 0 error. As you can see, 0 error. We don't have any error. Okay, we don't have any error. So in this way, we can try to see the location. Okay, the location of the error, and for example, in the same way, let's see the memory leak. Okay, we have memory leak here. So instead of this what we are going to do, we have mem leak here. Mem dots. I think we have another mem leak alpha. Okay, so let's see this what this will give us. As you can see in the memory leak also, too many memory error is detected. Not this one, and not this one. Mem leak, yeah. As you can see, memory error is detected. Heap summary, if you see in the heap, you see in use at exit 16 bytes in 2 blocks, and total heap usage is 3 allocates and 1 free, and 1040 bytes is allocated. If you see leak summary, definitely loss. This is what we are losing, 16 bytes in 2 blocks, and indirect loss, and other losses also here. And in this way we can check. Okay, in this way we can check. And I think what we can do there is let's use this code again. paste, and what I want to do, let's add here this formula, the leak full. Let's copy this and paste it here. Okay, paste it here, and let's see what it does. Sorry, it needs this one, needs space. Sorry. Here, space. Okay, as you can see, 2 errors from 2 contexts, and for list of detected and suppressed error, and as you can see, it gives us the error. So in this way, you can use the memory, this bug grind, and you can detect your memory leaks and memory problems. And I invite you to download the course. As you can see, we have a lot of course: buffer overflow, no mallocs, corrected ones, no malloc corrected, and double free memory leaks, dangling defects. All these things we have seen. So let's go to our presentation, and this will be the system code related to memory allocation. Okay, that's what we are going to soon. So as you can see, we have break and sbreak. These are the 2 commands we have. Malloc library call as break system code, and break is called to expand the program breaks in the heap and break the location of the end of the heap in address space. Sbreak is an additional call similar with break, and programmers should never directly call either break or sbreak. So one such system call is called break, which is used to change the location of the breaks, the program's break, the location of the end of the heap. It takes one argument, the address of the new break, and thus either increase or decrease the size of the heap based on whether the new break is larger or smaller than the current break. So it will increase or decrease our heap size. Okay. In addition, call sbreak is passed on increment, but otherwise serves a similar purpose. Okay, passed on an increment, but the same purpose it will give us, because it will give additional. Note that you should never directly call either break or sbreak. They are used by the memory allocation library. If you try to use them, you will likely make something horrible, wrong. So stick to malloc and free instead. That is a recommendation. So let's continue. So we have a lot of system calls. This is the break and the sbreaks are some of the system calls that we okay. So let's continue. System call related to memory allocation. Again, we have mmap. This is another allocation. This is the syntax. You can go to the man page and you can see what is mmap. System call can create an anonymous memory region. Read the man page for more information. So this will create another anonymous region in our memory. Other memory APIs call alloc, calloc. This is also the syntax. So allocate memory in the heap at 0 seat before returning. So the argument, as you can see, size t and size t num and size t size of each blocks in bytes, number of blocks to allocate will be here. Return success, a void type pointer to the memory block allocated by call alloc. Fail, a null pointer. So, other memory APIs, realloc. This is the syntax, realloc, void pointer size t, like this. Change the size of memory block. Okay, this will be changed because it will reallocate it. The pointer returned by reallocate may be either the same as pointer or any one. The argument, as you can see, void ptr pointer and size t. So pointer to memory block allocated with malloc, call this calloc or realloc 3. Okay, the size t, new size for the memory block in byte. Return success, void type pointer to the memory block or it will fail. So in a nutshell, that was chapter 14. We have seen different system calls and the break is breaks, and we saw also valgrade also for the memory leak and other types. And I advise you to download and use it for yourself. If you don't have it, you can use sudo snap install valgrade classic and you can play around and check. Purify also another one. So all the problems associated with the memory were discussed in this double and dangling pointers, memory leaks, and other forgetting to initialize and not allocating enough memory and forgetting to allocate memory. All these things were discussed, and the syntax of the code from this book was also discussed. So I hope that this chapter was helpful, and I recommend you to read the book as well and the code, download the code and play around, and you will be okay. So that was it for this chapter, this Engineer Selassie. Okay, from Yellow Academy in Pen Boosters. We will meet in the next chapter. Till then, bye bye. Thank you.